It's hard to clap for the second time, I understand. So tonight, there's something this is a tool I've been using at work for the last couple months, and it's super cool, and I've just been so excited by it and how great it makes each and every day at work that I really wanted to share. I know, you guys are laughing, but it's really true. It's so cool. And so I wanted to come in here and show you guys about it so you can maybe join me in super fun land. And the name of this tool is Storm. I know this is confusing because there's also like a Python ORM called Storm. I'm not talking about that. This is a framework for distributed real-time computation. So yeah, what is it? Well, as I just told you, it's for real-time computation system. It was created, Nathan Mars, who's a very smart guy, kind of saw this need when he looked at systems like Hadoop. That we had this ability to batch process enormous amounts of data, right? But there was sort of this gap that if you needed to understand your data, in a more real-time fashion, and you couldn't wait necessarily for that, the entire MapReduce job to run, that there was sort of this hole that he identified there. So that's sort of the impetus for the creation of Storm, although as a generalized problem, it turns out that it's really good for all kinds of things like DRPC and a lot of like your current SOA needs, perhaps. It's distributed, so it's going to run on a bunch of computers. It's fault tolerant, so it understands that you're running on a bunch of computers and some things are going to be bad because life is bad sometimes. And the tie-in for ChiPy is that you can actually use this with any language, so it's super exciting. Okay. So this is sort of a lot like what my life looked like before I knew about Storm. So we had like the world, and the world always wanted to call my public API. And then my public API was pretty dumb. It would just like drop something on Rabbit. And then there'd be like some service, and it's like a bunch of services reading from Rabbit, and like, oh man, let me go look up your customer data or something like that. And then I'll go drop something else in Rabbit. And then I'll have another service pile that'll pick some stuff up, and maybe they'll like, call somebody or start, some alert chain or whatever, and then drop it on a couple more Rabbit queues. And this was sort of, kind of how I composed, from small pieces, solved my big architectural problems, And it's a step forward from a massive monolithic process that I had before this. Like my life before SOA was even worse. It was just a one box, right? But this is still comes with some drawbacks. So what did I spend my time doing there? Well, I spent a lot of time standing up message queues and services. I spent a lot of time fiddling with config between message queues and services. I spent a lot of time writing endless monitors because, like, sometimes a message queue or service stopped. I had to write all kinds of automated recovery tools because when, like, it stopped, I didn't want to get called at 3 a.m. to start it again. I had to devise all kinds of plans for tracking messages through this system. What happens if it gets halfway through? How do I know that? How can I get it the other half of the way through? I had to have all these integration environments I was building because it was very difficult to set up that whole thing on my laptop where I wanted to develop. I had to create these elaborate deployment plans of like stopping like this one part in the middle, and then like worrying about how much queues we're going to back up, or like the worst thing ever, if you changed the message format of a queue, you'd have to like ETL between queues. So I mean, oh, and sometimes I might actually have time to write the business logic that I was supposed to be writing. And so, I mean, it's cool that I could do this, but there was a lot of administrative overhead. We already have a hand. Yeah.
I just want some context, like what kind of problems do you kind of set up, just so I can kind of apply to a real world situation?
Yeah, okay. I don't know if I can really name all my employers that had some, like, let's say, a category of problem. If you have like a device, like a sensor embedded in like several thousand factories, right, and they're emitting, hundreds and thousands of readings, multiples per second, right? And you're trying to store that and like find out things like maybe one of them is on fire, right? And you don't necessarily want to wait for a MapReduce job to run to tell you that it's on fire. That's the kind of thing that started to be addressed with like this kind of an architecture, right? I mean, I'm pitching it in more general terms of there's a service and it's looking up customer data, but those were the kinds of things that I saw thrown at architectures like this, right? Okay. Oh, okay, things Storm does for me. Well, okay, first off, some Storm terminology. We've got spouts and we've got bolts. A spout means it's a source of data. A bolt means it's doing something with that data. And Storm manages all those messages between bolts. So before when I was talking about managing all those rabbit queues, whatever, Storm is on top of that. It manages bolt health. So it notices, hey, it looks like your bolt fell over. It seems like you may need that restarted. How about I do that for you? And that's really cool. So it does that for me too. It's going to manage deployments for me. So it's when I tell it to stop a topology, it'll halt it kind of in a sane manner, and then let me deploy a new topology. It will, and this is like the coolest part about Storm, is it tracks messages. It can guarantee that a message is processed at least one time by your system, which is awesome. And so you can get reliable message processing. And another benefit, it's actually really easy to run locally. It's trivial for me to run this whole thing off my laptop. Okay, so I'm going to contrive an example because I know you want to hear context, and so I'm making something up here. And it's a little bit silly, but I didn't really have the time to code you something like super spiffy. Okay, so kind of imagine that the problem is a little bit harder than I've made it up here. So we like to think about Storm topologies as a directed acyclic graph. I forgot to draw arrows because I forgot about the D in the DAG, but there are supposed to be arrows. And so when we imagine a topology, here we have like a sensor, okay? And maybe the sensor is emitting two different kinds of data. It's emitting a temperature reading and also like a pressure reading. Okay? And because this example is silly, it's doing it in Fahrenheit and atmospheres of pressure. And so the first thing that we really want to do is we want to split that data stream and say, okay, if your temperature data go this way, and if your pressure data go this way, and then we're going to convert temperatures into Celsius, because we just like Celsius, and we're going to convert pressure into millimeters of mercury. Okay, cool. That's done because we just calculate things for no reason and then ignore them. This one continues on. It says, first, let's go store that in the database. Also, we're going to, in memory, kind of calculate an average temperature, which is a really cool problem, because if we're doing this in memory, and we said, hey, Phil, didn't you say that this is going to be run over this topology on your network? Then you need to start worrying about maybe getting the same sensor reading to the same worker. So that because if you send this, if you've got sensor number 1 and he sends, the first reading to box A and the second reading to box B, well, your average isn't going to look sane, right? Because half of it's in one place, half is in the other. So there's an interesting problem to solve there. And then maybe, if this thing is too high, the temperature is way too high, we're going to send an alert. So this is sort of the contrived example that I made up. And to demonstrate like the Pi part of this talk, these two portions of it I'm doing in Python, and these portions of it I'm sort of doing in Clojure because it's awesome, but not as cool as Python, of course. Okay. Great, okay, so I've given you the context. It's time to go see some code. The fun part. Oh yeah, I already showed you a graph, but I have a coworker who likes to make graphs too. And so he made this for me, and it jiggles. So this is another direction, and this graph got it right. You can see this one actually has the arrows. So that's, again, what we're about to look at, in case you wanted a jiggly version. I'm glad my coworker also likes my jokes. It's like the best part of working with him. Okay, so this is Clojure. I know it looks a little funny, and it's also off the screen a little bit because I was trying to make it big enough for everyone to read. We're going to go through it a little bit slowly. You don't need to know too much Clojure. Oh, I didn't mention, I'm sorry. So Storm is running on the JVM. That's why we're talking about Clojure. So you can actually run the whole thing in Java, okay? And if you're anything like me and you pull Java code, you wish that you didn't pull Java code. And so that's why I'm going to talk to you about Clojure, because first off, it fits on one screen instead of like 8,000 screens. And second off, it's really cool. Okay, and so when you look at Clojure, almost everything, like a surprising amount of your code, looks like just structured data that's just hanging out. And so that's the important part that we're going to basically talk about in this talk, is like just kind of data hanging out. I'm not going to do all kinds of crazy lambdas, blah, 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 blah. Okay, so thinking back to that topology, there was the spout part, which was the source of the data. And so over here, we see, so the curly braces, oh, maybe I should highlight code, that'd be better, rather than Phil pointing and stopping you guys from reading. Okay, so the curly braces, this means we're in a dictionary. Well, that doesn't look so bad. Okay, and so the key to the dictionary is this string that says sensor spout, so I gave it a friendly name. And then what is the value? It's this spout spec thing, which is just the name of like some macros. You don't have to worry about it. And then the implementation of that thing. This little comment I put off here to the side is to try and show you what the output of that spout is. Because if you'll remember, I was saying that there's two different types of reading. So I'm saying over here, there's one output which is going to be a temperature stream, which is a tuple, right, of like time, ID, and reading. And we're going to have another stream called pressure stream. I'm sorry, I went to the wrong way. Okay, we've got this pressure stream, which is also a tuple of time, ID, and reading. Okay, cool. So, Phil, that's where the data starts, and what are you going to do with it? Well, over down here, we've got these, this bolt map, okay? And so for the bolt map, again, I've given it a name, convert to Celsius. And again, it's a bolt, okay? And what are we doing with this bolt, Phil? Well, I'm going to take in sensor spout, right, our friendly guy up there. And what part of sensor spout am I going to take in? I'm going to take in just the temperature portion. Cool, so that's how I split it up. What am I going to do with it? I'm going to call this convert to Celsius guy that I wrote. This P2 is like, I'm hinting at the parallelism, so I'm saying, let's talk about two workers on this guy. Okay, cool. Convert to, from atmospheric pressures to millimeters mercury, looks pretty much the same as the convert to Celsius guy. And then down here to the super fun part, it's time to set alarms. What am I going to do? Well, instead of this bolt spec, I got this shell bolt spec. It takes the stream convert to Celsius. This shuffle algorithm, that's like find somebody who doesn't look too busy and give it to them to work to. So it's kind of like round robin-ish. And what am I going to do when I find a worker who's not busy? Well, I'm going to call Python with setalarms.py. And the output I'm expecting is a tuple with the ID and Celsius. And I'm going to give it degrees of parallelism 5. And so same thing with running average. This one is super cool because if you'll remember, I'm saying I'm calculating running average in memory. So I need to worry about, now I just can't send it to anybody. I want to send the same sensor to the same worker every time so that I can keep this in-memory average running. And so that's just that ID. Like, it's just that easy. I mean, the amount of power we're deriving from this topology here, and you can tell, like, this isn't a lot of code. This is mostly data. It looks a whole lot like, you know, drawing boxes from a certain extent. Anyway, back down Python, running average, ID average, and then finally just storing it. I'm going to store it in a database. And like, that's the totality of the topology. So if you wanted to do everything else in Python, this would be like your extent of Clojure is just this file. And everything else would just be like a shell spec bolt and a Python thing. And you'd be done with the Clojure code. So I'm going to delve into a little bit more detail on some of these, just because I think it's pretty neat, and I'm hoping you find it as neat as I do. Did you have a hand up, or were you stretching? Oh, I'm sorry. I just stopped the whole talk. Yeah, why am I showing the Clojure? Right. Next question. Okay, so this is going to look a whole lot like Lisp because it's Clojure. So I'm not going to delve into it too long, but if you did want to write things this way, it's basically as easy as saying, hey, this is a spout, and I'm going to go like emit some things from the spout, and that's about it. So you can see I'm emitting two different things. You know what? We'll move on because you guys don't really care that much about it. But the code is available on GitHub if you do decide to care at a later date. What we will look at, however, is the Python part of it. So over here in multi-lang resources, we've got that running average and set alarms, and we've also got this storm PY, so we're going to start here. This is code that was provided for us. You can definitely hack this to do an even better job. This just sort of gets you off the ground and running. So there's a careful specification delineated of what it takes to sort of communicate messages between bolts using Storm. And to get you started, they wrote one of these for you for Python. And so basically all it's doing is it's reading from standard in, and it's reading JSON that's been serialized out to it, and it's gonna read that in and then call, what is it gonna call? Well, over here, let's take a look at set alarms. So from that other file, I now have my set alarm bolt, right, which is a Storm basic bolt. What does it do? It's gonna take a tuple, okay? So I destructure the tuple, we get that sensor ID and temperature. I say if temperature is greater than 22, oh my gosh, it's an alarm, crazy, okay? And then we go to this emit, all right? And again, the reason of the emit is we're not just returning data, but it's helping it track data through the whole system. So when we emit these things, it can say, hey, this guy did the right thing and he's done. And that's how easy it is to write a bolt in Python. There's not a whole lot of code, well, in this example, but I mean, the boilerplate that makes this thing go is not that great. The other examples may be a little bit more interesting of running average. Okay, so here, right, when I've got a running averages, right, and so when you get a new tuple, that is a sensor ID and a temperature, if we already have it in the dictionary, I'm going to pull it out and compute a new running average and then put it back in. Otherwise, I'm just going to put whatever the count is 1, so that's also the average. I'm going to put the 1 and the new average in. And then just log it and emit it. So that's pretty cool too. Oh, let's actually see this thing run. That would be exciting. Maybe. Yeah. What about light table? What about light table? Okay, so my coworkers remind me, light table is in alpha. It supports both Clojure and Python. It has a bad habit of sometimes crashing and sometimes destroying the JVM. Let's not talk about that. So my coworker admitted, it suggested that I quit it before I run it so it doesn't accidentally take down my demo. So thank you. All right, so I'm going to run this for a second and then stop it so we can just kind of take a look at the logs, because logs are so exciting. Like, I know, like front-end people have like shiny things to point to, and back-end people point at logs. And I'm like, oh, it's so great. Okay, so cool. So let's take a look at what just went on here. Let's take, here's conversion. Okay, so here we've got, we're hitting at the conversion bolt. We've got the ID, temperature is 3. We converted it to 28 degrees Celsius, and then sort of in parallel, it went to store it, because that's what we're going to do. It also hit that shell bolt, which is Python, and you can see this log message here. That was that log statement in Python, made it back into our logs. And what's even worse is, oh my gosh, it was higher than 22 degrees. Alarm! Okay, and okay, and that's all pretty exciting. Let's see if I can find an average calculation. I might have needed to let it run just a little bit longer to get a better average. I'm going to start it one more time. While that's running, though, I'm going to show you another super cool thing about Storm, which is when it's time to actually deploy, how cool it makes your life. So there's this Storm UI. And hey, that's pretty cool. What we've got going on here is it's going to tell you, I've got, and this is also in the repo, I spun up a Vagrant box, and I've got like the world's worst shell script to configure it, but it does work. What it's going to do is it's going to install Nimbus and Zookeeper and Supervisor, which are sort of the components that Storm is using to keep this whole thing running and talk between it. And then I uploaded it, this demo topology, which is the same thing that we just stepped through. And so when you look at it, did I just bring it down? This is like I had stats showing, and then I hit some buttons, and now life is bad. Oh man, it's really disappointing. Okay, well, there were numbers a second ago, and that's like the worst rule of live demos, is that sometimes you screw them up. And what they mean is this. Let me stop this thing. Lost my mouse. Okay. I'm really sorry that I somehow killed my stats. But what they would do, if you saw them here, is you would see every one of those bolts that we just talked about would be listed here, and then we could see how many messages it's transferred, how long it's been taking to process each one of those messages, how many messages have been acted through the system, how many have failed. So if you see that we're getting a lot of failures, even though it's going to retry Storm, well, Storm, if you tell it to, will retry, it starts to give you an idea of maybe there's like a big problem in your network because there's like a lot of things being retried. And so it's really cool because you can build all kinds of alerts and get a very good high-level view into your whole system. And again, this is sort of one of those things that comes for free with Storm. So the last thing I'm going to show you then is hopefully this terminal got enough data that I could show you an interesting running average. Just to show you that that thing actually worked and I wasn't lying. Oh, here we go, new average. Okay, so here's, this is like proof by induction, so feel free to ridicule me. But we have for sensor temperature 1, the new average is 21 degrees recorded over 24 readings. And then the very next one, sensor temperature 1, the new average is blah over 25 readings. So theoretically, if I was going to 2 different locations, we wouldn't have seen like an increasing, we'd see like temperature 1 is 21 and then temperature 1 is like 52 or something because they would have gone to different places. But I submit to you, this to you as some sort of evidence that I did the right thing and piped them to the same bolt. And that's it. The one last thing that I'm not really going to present to you but tell you about, when I was writing up this talk, I found this library, which if even like that brief closure part is too much for you, this library supposedly lets you write that part in Python. I haven't used this library, so I can't tell you if it actually does that. But if you're interested in the technology and like 20 lines of closure is like too painful, this might be a solution for you to check out. Okay, any questions? Yeah.
The part where you're splitting the parallel out, I'm assuming that with the zookeeper, this like runs all of those jobs and then like does use zookeeper to check that all of them basically going on results back.
Yeah. So you mean like this job is split into these 3? Is that what you mean?
No, I mean each of the individual, like on the lines of the closure where you were talking about doing the calculus.
Yeah.
You gave a p plus 5, so I take that to mean it's having 5 parallel workers.
Yes.
And so I'm assuming that it's feeding the same input to 5 different workers, or are you saying that?
Oh, okay. No, that's not. Okay, you can do that actually. I'm sorry. Okay, yeah, you can do that. There is a way to sort of like broadcast to everybody. But so if you Google the Storm Clojure DSL, each one of these like data, because again, like this all just looks like data hanging there, but each one of these symbols or whatever has like a spelled out definition. So what I'm doing here is like the shuffle algorithm says just like pick one guy who doesn't look that busy. There's another one that says send it to like all 5 guys. So there's actually a lot of flexibility, or in some cases, like this guy down here, I'm neither going to send it to all 5 guys or shuffle. Even if one guy is really busy, if that's the guy who keeps track of sensor number 1, always send it to him, because I told you to group on ID. So there's a bunch of different ways that you can sort of manage that. Yeah.
Repeat the questions.
Okay.
What's the underlying transport for moving the tuples around?
Yeah. So if you're within, what is the underlying mechanism for moving tuples around? And so if you're running, within the JVM, it's using 0MQ and it's using thrift to serialize everything. Now, when you do the shell bolt spec, right there, it's making a shell call and it's serializing it to JSON when it's talking to it. So that's a little bit different. Although I think you can change that in the implementation spec of like how you can write your own implementations. Yeah. Anyone else? Yeah.
Just a quick question about closure, or closure, whatever it is. It looks like where you've got here, for the syntax and the data types, you say you're bringing in tuples. what's the basic data type of that? Is it a list, like list, and those are just complicated data types that you're using?
Okay, the question is like, what is the data type in Clojure? Okay, so the way that the Clojure layer here is the layer that I like to deal with. It's built on top of a lot of very interesting objects in Java. So I don't really want to talk about the Java part, other than the Java part's a little bit more complicated. But because of that, the docs always tell you that you're dealing with tuples. But in Clojure talk, right, like these like square brace things, this means that like we're dealing with like an array basically, or a vector, right? And like the curly braces mean that we're dealing with a map. And then like if you do like this, it means like, you know, like hi, that's like a list, right? So those are the sort of basic Clojure data structures. Although again, although they look like that here, how it actually handles it on the JVM is very unique. If you delve into the Java code, it's a little strange. Yeah. Yeah.
Right, so again, this would probably save both creating phone calls and headings of tracking and messaging. Is there any performance improvement in switching from your collection of processes and rabbit queues to this?
Yeah. Good question. So the question was, are there performance benefits to be achieved by swapping to this rather than the world of like a million rabbit queues and services? So I don't, let me start by giving like the easiest answer I can, which is I've never built the same system in both and then performance tested them. The communication between bolts in Clojure is really, really fast because the serialization is really good and 0MQ is pretty cool. But like, you know, again, is that going to be faster than something you could achieve with like, you know, super good rabbit tuning? I'm not sure. Some of the things, and this is maybe not like a strict performance gain, but maybe it leads to performance gains, is that view of your system in the Storm UI actually makes it a lot easier for people, especially people on a time budget, to do a much better job of tuning their whole system for better performance, because it's easy to identify where the bottlenecks are and where you need more workers. So it can lead to some good performance gains, although, again, you know, somebody who spent their whole life tuning it with Rabbit, you know, they can do a great job too. Yeah. Last question. Yes?
So what sort of performance do you get from just like messages per second or scaling?
Okay, so that's a great question. We can scale it quite a bit, and we're not scaling it right now very much. We're running it, you know, aside from on my laptop, on Amazon Web Service, and our peak load right now for it. This is a little bit of a big hammer. Our peak load for it right now is maybe only like 10 messages a second, which this thing like does like while like laughing at you. It can do way more than that, and the reason why we're using it in part is because we anticipate our traffic that we're putting through it to be much higher in the future. I wish I could tell you the best production success story in the world. Twitter is, okay, thank you. Twitter is also using this, so they've got like a people who are using it list. Thank you. Lots of people are using it with much higher capacities than we are. For us, this is a planning for the future based on what we're projecting our traffic in the next like 2 to 3 years to be scenario. So yeah, I wish I could tell you like 1 million per second. Nathan Mars said 1 million per second, so I trust him. So there you go. All right, and that was the last question. So thank you, everyone.